Hi, I wanted to talk about a problem that we gave as an exam problem last year in this unit on 2D physics. And this is a problem that involves the force of gravity as a centripetal or center pointing force. So this is a problem about the International Space Station. It's a space station, a spaceship about the size of a football field. It's continually staffed by astronauts, ranging from 3 to 9 at different times. And we get there using these Soyuz rockets and capsules that are launched from Russia. It orbits at an altitude of about 240 miles above the surface. So one of the things, if you look at the orbital diagram on the left there, you'll see that it's greatly exaggerated. 240 miles is pretty small distance compared to the size of the Earth. And so I've already sort of over-exaggerated the size of the orbit. It should actually be a little bit closer to Earth given that scale. The station has a mass of 450,000 kilograms, and we're going to have it orbiting in the counterclockwise direction as seen from above the North Pole. That's actually pretty common because folks like to launch spaceships and satellites taking advantage of the fact that the Earth seen from above turns counterclockwise. You don't want to try to launch something against the rotation of the Earth because you get that little boost from the rotation of the Earth. We'll assume for the sake of this problem that the orbit is circular, that it exists parallel to the equator of the Earth, and that the speed of the station is constant. None of those are actually 100% valid assumptions, but I think they help to make the point, and then we can always make it more complex later. The first question asks us to diagram the directions of the velocity and acceleration vectors at one instant, and the second diagram the second problem asks us to calculate the force of gravity, the speed of the station, and the amount of time in minutes it takes the ISS to orbit the Earth once. So the first thing I want to do is part A, where I'm just going to talk about the dynamics or the kinematics really of the orbiting spacecraft. Now, one thing that people often don't know is, when you're trying to get into orbit, you got to get up high in the air. You got to get up about 240 miles, which for a rocket, that's not that far, right? Most of the sort of thrust and energies, stored in the chemicals that are combusted to create thrust are used to speed up the rocket in its motion. So actually the velocity of the rocket is extraordinarily high. Here's its velocity vector, tangential to the surface of the Earth. If it didn't have that high tangential velocity, it would just come back down. Like if you just launch straight up, there's still gravity. The gravity extends infinitely far out, but certainly as far out as the moon, which is way off the screen as seen here. So the ISS feels essentially as strong a force of gravity as it would on Earth. 240 miles is not that far compared to the radius of the Earth. And so it would just come back down if you launched it straight up. What it needs is this really enormous tangential velocity. I might mention that the magnitude of this velocity, so the speed of the International Space Station, is the distance it travels in one orbit, which is 2 pi times the radius of its orbit, divided by the period of time that it takes to go around. So if the radius is in meters and the period is in seconds, this gives us a speed in meters per second. This is distance over time. Now this assumes our circular motion, but that's fine. Okay, so now as we saw in class, as the velocity varies, so here it's going this way, here it goes this way, here it goes this way. Whoa, I just moved my window by accident. Here it goes this way. The acceleration is centripetal, it's center pointing. And so the acceleration is towards the center of the Earth, and that acceleration we saw can be calculated as v squared over r. And if you wanted to, you could plug in this v right away here, unless you needed to calculate the speed of the station, which we of course do. So, but that's something you can do for simplification purposes at some points in your problem, is just plug in that velocity right away. So the International Space Station is always accelerating towards the center of the Earth. Its velocity, therefore, is always turning towards the center of the Earth. But because the velocity vector is so great, it's so long, the magnitude is so high, the turning actually, it turns over some long period that allows it to sort of keep missing the surface of the Earth as it goes around, and that allows it to maintain an orbit. So the International Space Station is constantly falling towards the center of the Earth, but never hitting it because of that high tangential velocity. Now, if we wanted to calculate the force of gravity acting on the ISS, remember that the force of gravity calculated by the universal law of gravity, because we can't just use mg in this case because it is 240 miles up. We're going to use the Newton's universal law of gravity, which involves a gravitational constant, the mass of the Earth, the mass of the International Space Station, over the center-to-center distance squared. Now that is the distance from the center of the ISS to the center of the Earth. That's also the radius of the orbit. So that r is the same as this r, which is the same as this r. That's good. Now again, that r is not 240 miles because that's just the distance from the surface of the Earth. So we're going to have to add 240 miles to the radius of the Earth. So the radius of the Earth plus 240 miles. And I can leave it to you to use Wolfram Alpha to convert everything into meters, especially that 240 miles. The radius of the Earth you can probably find in meters. And that'll allow us to calculate then the force of gravity, because we can look up the mass of the Earth, we know g, we know the mass of the International Space Station, and we know the distance squared. Now, the next part is for us to calculate the speed. So that gives us the force of gravity, and that's doable. The next part is to calculate the speed. Well, we could try calculating the speed using this equation up here, but we don't know the amount of time. In fact, that's the next thing we have to find. So let's do it this way. We know that the force of gravity is the only important force acting on the space station. Sure, it has little thrusters, and sure, it's hitting a little bit of atmosphere, and so it has some drag, but those are negligible compared to the force of gravity. But we know the force of gravity is centripetal, so we can set the force of gravity equal to mass times the centripetal acceleration. The reason we can do this is that this is the net force, and the net force equals ma, and a, when you're moving in a circle, is v squared over r. Now, you can do a nice cancellation here. The mass of the space station cancels. That's the thing feeling the forces, and it contributes to the gravitational calculation, which means that, this is an important point. If somebody steps out of the International Space Station, then they're in orbit just like the ISS around the Earth, but fortunately that orbit doesn't depend at all on their mass, or they would be left behind or fly in front of or something the International Space Station, but of course they just follow along right next to it. This is this idea that the inertial mass and the gravitational mass cancel. Just like on Earth, all things fall at the same rate for the same reason. Now, we know the radius of the orbit, we know the mass of the Earth, we know g, we know the radius of the orbit, so we can calculate the speed in meters per second, and then of course we can convert that to miles per hour using something like Wolfram Alpha. And so that would give us the velocity of the orbit. The final thing that we need to do is we need to calculate the amount of time in minutes it takes the ISS to orbit the Earth once. Well, that brings us back up here. We now know the speed, we know the radius of the orbit, so we can find the time period that it takes to go all the way around. So you'll see when solving these orbit problems, there are three related equations, all of which have to come into play. The first equation that we have to do is we have to consider what forces are acting on the object in orbit. In general, this is the gravitational force. Then we have to say, what kind of orbit are we creating? If we're creating a circular orbit, then we know two things. First of all, we know the speed in orbit as related to the size of the orbit and the period, and we also know the acceleration in that orbit. I recommend, there's a bunch of equations you can come up with from this. For instance, if you see in the reading in the textbook, there's Newton's form of Kepler's third law that basically solves these three equations for a relationship between r and t. That's cool and everything, but I kind of think that you should just start with the basics. These three equations and the model underlying them for circular motion are the basics, and you can do everything that you need from there. I hope this video has been helpful. Thanks a lot.